Consider the forces on a skier who has come to a sudden stop. The box represents the skier and his equivalent mass. The forces that keep him in equilibrium are his weight, W, the support force, S, supporting his body, and frictional force, F, preventing him from sliding down the slope. The forces intersect at the same point, and the vector triangle shows there is no resultant force. Now consider the components of the weight, W, parallel to and perpendicular to the slope. By resolving forces at right angles, you can see S equals W cos theta and F equals W sin theta. Consider the forces on a skier going up the slope on a drag lift. The forces that keep the skier in equilibrium are his weight, W, the support force, S, supporting his body, the tension of the tow rope, T, and frictional force, F, down the slope, as the skier is now moving up the slope. Now resolve forces parallel to the slope. As the support force is perpendicular to the slope, it has no component parallel to the slope, so can be ignored when resolving parallel to the slope. Now draw the components of the forces parallel to the slope. As the skier moves up the slope at a steady speed, the forces are balanced. W sin theta plus F equals T cos alpha. Finally, consider the forces on a skier accelerating down the slope. The forces are his weight, W, the support force, S, supporting his body, and the frictional force, F, up the slope, as the skier is now going down the slope. As the vector triangle shows there is now a resultant force, the skier will accelerate. The force vector needed to close the triangle is the resultant force, which causes the skier to accelerate down the slope. This force is equal to W sin theta minus F. Using Newton's second law, you can write W sin theta minus F equals ma, where m is the mass of the skier.